Welcome back. The goal in this video is to introduce you to one of the primary tools in text processing, the regular expression. Of course, we'll also introduce a Python package that can be used to evaluate regular expressions and discuss regular expressions in pandas. Regular expressions are a tool for searching through text and extracting text. They allow us to succinctly specify a pattern using a code-like syntax. Essentially, regular expressions are a special code for a text processing engine called a parser. The idea of a regular expression comes from a programming language theory known as a regular language. Regular expressions were designed to make it easy to specify exactly what types of strings are valid parts of a language, which is important for parsing programs and turning them into machine code. But over time, this has become a term we use to describe how to recognize and extract information from text. We can write regular expressions, which are text themselves, and then hand that expression over to a regular expression engine, which turns it into an algorithm for recognizing text patterns. In fact, you can even compile regular expressions into code for faster processing, much like a program can be compiled. Regular expressions are also somewhat portable between programming languages, because they are a language themselves. Particular regular expression engines, however, do vary by language, but there are enough similarities that you should be able to read a regular expression in most languages. A great tool to help us study regular expressions is regex101.com. It provides a sandbox where we can type text in a regular expression and then see what text matches. It also even supports a wide variety of programming language implementations, documentation, and it can even generate code for us. For that reason, I suggest that you don't jump immediately into Python code when trying to figure out a good regular expression. Rather, you should spend some time working out possibilities in a tool like regex 101, and then once you're satisfied with it, test it in Python. The first thing I'm going to do is change regex 101 into Python mode. Now it's in Python mode. This way I can ensure that the documentation, the quick reference listed here, and the engine matches what I'll be using. Now I can type the regex. I'll type ABC up top. You'll notice that there's an R in front of the text string. This is an actual Python literal. The R, as we know, stands for raw string, and it's convenient because regular expressions tend to use a lot of backslashes. By using the raw string, we can avoid unnecessary escape sequences. It's also convenient that the raw string and regular expressions both start with R, so that you can sort of think of a string that starts with R as being a regular expression in Python. The most basic thing you can do in a regular expression is match one character at a time. Regular expressions read left to right, A, B, C. And so if you have the sequence ABC, that will match exactly ABC and ABC only. We can type that in this box, and you'll see it highlight when we finished up A, B, C, and now it's highlighted and saying one match. Now this is currently set into modes known as global and multi-line. If we click over here, you can see it's not going to return after the first match, and multi-line meaning that the start and the end of the line are determined by special things called anchors, meaning that's going to work once per line. And so if I type ABC on the next line, it's going to have two matches, and so on and so forth. I could type hello ABC and ABC would match. And so if I didn't have these on here and I left off global, you can see it'll only match the first one. And so it's essentially just match what I'm trying to type in here. And that allows you to test regular expressions that have new line characters in them. Okay. So now a regular expression is overkill for searching a string for an exact sequence of characters. We can already do that with the in operator. Where it shines is when you want a flexible match that can include many text strings that all fit a pattern. For flexibility in single characters, we have a few options. You can see those in this table over here. Just a single character C would match. We've already seen that with ABC. But you can also put, for example, a dot, and that will match any single character except the new line. And you can see there are a number of other options here. The ones that are particularly useful are things like any white space character or non-white space character. Digits are extremely useful, and then anything other than a digit can also be useful. And then lastly, you sort of have a compilation of those that are the word character classes. So the letters, numbers, and the underscore is included in that. And then you have non-word character classes like parentheses and apostrophes and things like that. And finally, the new line. I'm going to skip back over into full screen so you can see this clearly, but let's play with a few of these patterns. So let's say we wanted to match ABC, but we also wanted to match ADC. You'll see that right now only ABC is matching. We have a few different options, but one option that I can do is say A dot C, and that means match the character A, any character, and then C. And so ABC works, ADC works, A space C works, A apostrophe C works. Now, a lot of times what you'll do with these test strings is you'll include positive and negative examples. So let's say we only wanted to match ABC or ADC. Well, for that, we can use what's known as a character class. And so we can put in brackets these particular letters that we want to match, B, C, D. And now that'll only match ABC and ADC. It won't match anything else other than that. You can see ADC again. We could do any digit between those. So \D would only match something like A1C. It won't match ABC anymore. Or we could say we wanted, for example, a space, and that's it. And so a space C is matching because we deliberately put a space in here. But if we wanted to do any white space character, we could do \S. And so you can see this matches. This will also match a, well, if I could type a tab, it would match a tab C. A new line C is matching that though. So that's considered a white space character. So lots of different options for single characters. A really nice one is the character class where you can put a dash. So I can do capital A to Z, and this will show you that this is case sensitive. And so none of these are matching right now. But if I type AAC, it'll match. Or I can type AJC, a lowercase AJC, and it'll match. And so you can put a dash and put characters in between these. Another really useful thing that you can do is to put a caret at the front, and that'll invert that. And so this is matching not A through Z. And so now you can see only ones that are not matching here are the ones that are not in A through Z or have more characters than are required. So all the other ones are matching besides these. Lastly, if you want to match a dot or a backslash, then you need to use a backslash in front of those. So if we wanted to match a \C, then you would need to match that with \\. So you can see the single \C matches. And the same would be true for a .C. This would be a .C. If you should just put a .C, that would be the special character code. So a \.C. You've got to use an escape sequence. Where regex starts getting complex is in matching multiple characters at a time. And I'm going to start using the word tokens because these work beyond single characters as well, such as matching groups flexibly, as we'll see in the next slide. And so the way this works is with the following patterns. Given a token T, you can specify another character or either between or after the token, and that'll tell you how many you want to match. In the first case, we can put a vertical bar between two tokens, and it says I want to match either the token on one side or the token on the other side, but not both. If you put a question mark afterwards, it says that that token is optional. If you put a plus afterwards, it means that you want to match one or more of that token. Star is similar, or asterisk, and that means 0 or more. In both of these cases, you notice that I put this word greedy next to it. that means it's going to consume as many of those tokens as it can. And so if this is A plus, it's going to match any sequence of A's in a row. If you put a question mark after the plus or the asterisk, it means that you want to match as few as possible. The remainder of these are similar, except for you can specify exactly how many you want to match and the minimum number and the maximum number. And so TM, in this case with the curly braces, means you want to match exactly M of those tokens, or you can say I want between M and N, or at least M, but possibly more. And then you have variants where you could match a number of those where it's saying do this lazily. Let's investigate a few of these. Let's start with matching any two characters followed by another character, B, for example. So I'm going to say any character at least 2 times, or 2 times exactly, followed by B. So let's write AAB, that should match. CCB should match. CAB should match. ABCB will match, but only at the end. Let's say between 2 and 3. Now this one matches as well. What if we type 2 comma, meaning at least 2? So AB won't match, but AAB will. ABAB will. But now, what happens when we do AAB? What's going on here, this is only a single match. Why? Because we said 2 to anything. 2 to any number followed by a B matches, even if there's a B in here. If you want this to be 2 matches, we need to tell it that we want it to be lazy about it. And so this matched 2 and found a B, and it was perfectly fine. Then matched 2 and found a B. And so this is called a lazy match. We can also, of course, use the other quantifiers, which are more generic than these quantifiers. These quantifiers are very specific, but we can write something like A plus, and that'll match any number of A's. So A. And we can also use these with groups, and so we could match between A and Z, or A and F plus, and so this will match A, B, C, D, E, F, but if we put a G, that doesn't match. So that was any of them between A and F. Star would be any number, so we could say B starts with a B, any number between of A's through F's, and then let's put a G here. And so BAG should match, BAAAG should match, BG should match, because it's 0 or more. You can make things further complicated by using matching groups, because these groups work with the quantifiers as well. A group is surrounded by parentheses. This group specifies that you're going to see the tokens T1, T2, and T3 in sequence, and that those tokens are going to be a single group together. Another type of group is known as a non-captured group, where this one is a captured group, this is a non-captured group, and it simply begins with question mark colon. The last one type of group is a named capture group, and that begins with question mark, capital P, angle bracket, open angle bracket, the name of the captured group, whatever that you want to call it, and then close angle bracket, and then the pattern again. If you have a regular captured group, it's a numbered captured group. If you have a named captured group, right, you'll use this pattern, and you can refer to those captured groups later. So if you want to say that the pattern starts with some group and then ends with that same group, you can refer to the group either by number, \n in the case of a numbered group, which is probably the more common one to use, or a named capture group with parentheses, question mark, P equals name, close parentheses. Let's explore this. To start, we'll do a traditional numbered captured group. So for example, if I write ABC and then plus, that essentially says I want to match ABC, I want to match ABC, ABC, or any sequence of ABC in a row. And you can see how regex 101 depicts this. It shows you the matches and then shows you the groups in each match. And there's just one group in each match. Let's look at the non-captured group and how regex 101 depicts that. And so we can write question mark colon, and now you see we get the match, but we don't get groups out of the match. Let's look at the named captured group. So question mark P, open bracket, whatever name, close bracket, and you can see regex 101 again depicts it similarly to the numbered captured groups, but now gives it the name whatever name. Now, what's really powerful about groups is you can refer to them later. So let's say we wanted to match this group, or this sequence, ABC, then dot star question mark backslash 1. What this matches is ABC as a group, then lazily any number of characters, and then that original group again. And so what this says is that the string has to start with ABC, can contain anything, and has to end with ABC. It has to start with ABC, any number of characters, and ends with ABC. And so you can see the last match here is all of this for group ABC. So we can essentially ask the regular expression matcher to remember previous groups so that we can use them again. Finally, it's often useful to want to refer to where something occurs rather than in what sequence. And this can be done using matching anchors, which refer to specific landmarks in the text. One of the most common ones is to match at the beginning of the text. And so for that, you could say caret T. The caret specifies the anchor for the beginning of the text. Similarly, the dollar sign is the anchor for the end of the text. You're not limited just to beginning and end. You can say the beginning or end of a word with backslash lowercase b, or the beginning and end of a non-word with backslash uppercase b. And then finally, you can specify that a pattern, which is what's actually matched, in this case T1, appears before another pattern, which isn't matched, it isn't consumed, it's just specifying a location, or it appears after a pattern. Again, not matched, but specifying a particular location that this token T2 needs to appear after. So let's test some of these in regex 101. We can first start with the caret. So the caret says that the pattern must start at the beginning of the string. And so if I wrote caret and then capital A through Z, so any character that's a capital letter followed by dot star, what I've effectively specified is that I want to match only things that start with a capital letter. A sentence starts with a capital letter. Shouldn't match a sentence, shouldn't match a capital letter in the sentence. And so this is only going to match sentences that start with a capital letter. But what if I also wanted to match that it has to have punctuation at the end? Well, what I can say is at the end here, it must match, so dollar sign at the end, any one of the following. Let's do a backslash period. So remember, we have to escape a period. We also have to escape a question mark. And an exclamation point, I don't believe needs to match, but the question mark is a escaped character, but the exclamation point is not. So a sentence period should match a sentence, question mark should match a sentence, exclamation point should match. You aren't restricted to just the start and end, though. You can also specify something called a word boundary. So let's say you wanted to find mistakes where someone repeated a word. Now you might try to type something like this. So you'd say sort of anything backslash between with a space between it, and then \1. What this says is that I want to match anything, then some space, and then match that thing again. And so that would be sort of a repeated word. And you can see it kind of sort of works. But the problem is that it's not just matching words, it's matching any repeats and any amount of space between that. So you could say a boo, boo, and really any space. So any boo would match. But there could be words in front of here, and it would still match because the boo boo matches. And there's a lot of other things that are happening here. And so this isn't exactly what we want. What we want is a whole word. So to match a whole word, we can do a \b in the beginning and a \b at the end. And so this will match a whole word with some space and then that word again. And so this is matching a sentence because that's exactly what we want. A boo, boo would also match. And so word boundaries are useful for specifying that you want whole words typically. Finally, you can also specify the pattern as an anchor. So unlike a group, this doesn't directly match. So for example, you may want to only get a word that appears before a period, but you don't want the period itself. And so what you might write is \b \w plus, so any word character that starts at the word boundary, and then you can say I want after that to be a period. And so you can see it's matching sentence, but not the period itself. So you want the word that begins before a period. So lastly, we have regex with pandas. So we've already imported pandas, but we need a data frame to process. And so let's create one quickly. pd.dataframe. And we'll do a np.random.default random number generator dot random, and we'll get a random set of 10 by 3 numbers. And then let's do some columns here. And sorry, this is a tuple. And let's get some columns. And the columns that I'm going to use here are a list of names. And I'll give a simple temporary string name here. But the other one's going to be year underscore 2000, year underscore 2001. And I'm doing this intentionally. And so we can see what this data frame looks like now. Got this random list of things. And so column labeled A, and then year 2000, year 2001. So a few different things you might want to do with pandas. One of the most important ones probably is to grab specific columns according to a pattern. And so if you write df.filter, and then you put regex, write regular expression, and you provide the pattern that you're looking for, you might want to do something like year. And if you just provide it like that, it's going to grab only the columns that are in that have that match, that search returns true for a year. You could do only ones that start with year if you wanted to, so like a caret year, and so that would work. Or you could do only those that end in a particular date, for example, or a particular set of 4 numbers. And so you could say \d for $. And so that would only match things that ended with a 4-digit number. Okay, so that's one way to filter out just columns. We can also identify in a series contains a pattern. In order to do that, we have to actually get a series that contains a bunch of these. Now, one of the most useful things I think to do here is to take these and melt them. So we've seen that before. Let's do a df.melt. And we're going to do the ID vars as A, column A, and the value vars are going to be the rest of them. And so if we did a melt on that, you can see what we get here. We get a new series where we've melted those other columns into a single variable column and a value column, right? But now we have a string column that has some patterns in it that we can process. And so I'll call this df melted. And we can process that. So df melted, and the column I'm going to process is the variable column. And the way that we access the pandas regular expression functions is in str. We've seen that before, but str, and then we have various functions. So we have like does it contains. So if we can say contains, for example, 2000 on here, it'll return back a Boolean saying which ones contain 2000. And we could, of course, grab just those rows by accessing like this. So useful. Probably one of the more useful things, though, is to extract that particular value. And so we could write df melted of a variable. And we could say stir dot extract. And what are we going to extract? Well, you have to provide capture groups that you want to extract. And so I'm going to extract year underscore and then open paren, meaning capture group. And we're going to use the raw string again here. And backslash D4 and close. And so this should extract the year value. And you can see, indeed, we get that extracted. And typically what we're going to do with that is tack that on as a new column. So df melted of year is df melted of variable dot stir dot extract. And if we print df melted now, we should see that we now have a year column instead of year underscore that. And then, of course, we can do a substitute. And so another way that we could have done this is change our variable by substituting for nothing. And so year underscore for just the year. And so we could do df melted and variable here dot sub. And so we're going to substitute, dot replace, not substitute, str.replace. And we're going to replace a pattern, and so in this case year underscore, and we're going to replace that by nothing. And so if we do that, we should see that we get just back the year, which of course we could store back into the variable if we wanted to. Df melted of variable equals that. All right, so that's pandas. It's very, very powerful, and that's, of course, a vectorized function, so it's very fast as well. Make sure that you're using that .str. That's very commonly forgotten, and that will work on any column that is all string data. And I'd say the extract is probably the most useful part of this, where you can take a string data that's all formatted text and get just a piece of that out of that, or multiple pieces. And so if there were multiple parts of this, we could have used two capture groups in our extract, and it would have split it out into multiple columns. Now, just a few pieces of advice. You should definitely use regex 101 to create and test your regular expressions. Regex 101 is just one of many websites, but it's a particularly good one. And it can help you even find regular expressions for well-known patterns such as email addresses or phone numbers. Those already exist, they're well written, and writing them yourself is error-prone, so it's a good idea to reuse those. And also, you might want to consider various ways to improve the speed of your regular expressions, especially if they have to be applied across very large data sets. And two ways that you can improve them are using more specific, so usually longer regular expressions that say exactly what you want and exclude things as early as possible. You can also compile your regular expressions so that the regular expression engine does not have to interpret your pattern into code before it can actually use it. It can compile it once and then use that code over and over again. And so in summary, this video looked at regular expressions. From a high-level view, regular expressions reduce the amount of code needed to search through text to find patterns, and so they're a code-saving feature to avoid writing a bunch of loops and things like that. And the two libraries that we looked at were Python's RE package, and we've covered a few of those functions, but you should look at the documentation for the regular expression package to learn about all of them.
And we also use pandas, of course, which the pandas data frames and series functions have very powerful regex under the str property, and also under the filter property of the data frame for extracting information from text or for subsetting columns.